Okay, so this video is continuing in the Algebra and Linear Relations topic, but it's sort of the beginning of the second section within that topic where we look at linear coordinate geometry. So up until now it's been about linear algebra and linear equations. So throughout the coordinate geometry topic, there's a lot of formulas that come up. And sometimes students find this topic quite difficult for that reason, because the formulas are quite complex and they look ugly and they're sort of quite similar but different at the same time, and they get them mixed up. And they get parts of them mixed up and hence get the wrong formula completely. But what I want to really encourage you right from the outset here is none of these formulas are as complicated as they appear. And what's really important is you actually having an understanding of what the formula is doing and where it comes from, rather than just trying to rote, learn and memorize the formula. If you know what you're doing, you won't have to remember a formula at all. You just understand conceptually what needs to be done. And that's really the point that you need to get to here. As I said, if you try to just rote learn the formulas, you'll never be confident that you've remembered them correctly when you're in a test or an assessment of some sort. And you'll essentially just be guessing at whether or not it's the right answer. So please focus on the ideas behind what's happening rather than the topic as being a list of formulas. Moving forward over the next 2.5 years, 3 years of your maths study at school, there'll be too many formulas for you to remember. If you treat maths as a subject where you just need to learn and memorise and execute formulas, you're only ever going to get so far. And realistically, that's a sort of VCE further maths level of thinking about things compared to a VCE maths methods level of thinking about things. So we want to really establish understanding here, not just seeing a lot of rules to be memorized. So in this video we're going to be focused on gradient of a straight line, and also the equation of a line. There's a combination of different ideas throughout this particular video. So first of all, gradient. So the gradient of a line describes its slope. Okay, and gradient is rise over run. It's the change in the y value compared to the change in the x value. That's what we're looking at with this when we're looking at slope. So if we think about the following gradients, if we think about a line with a gradient of 2, we can write any number as a fraction. 2 is the same as 2 over 1. So we can think about this as being a rise of 2 for every run of 1. So meaning, for every 1 step to the right that I take, I'm going to need to take 2 steps up. And that will be a line that has a, let's try and get it actually going through this point, that will be a line that has a gradient of 2. Okay. If we have a gradient of 1/3, we can think about the 1 as being the rise and the 3 as being the run. So that means for every 3 steps across, we take 1 step up. So thinking about 1, 2, 3 steps across and 1 step up. It doesn't matter what units are used in those steps. They could be enormous steps, they could be tiny steps. It would still be the same slope as long as they're the same size steps, 1, 2, 3 across and 1 up on a smaller scale. Okay, I've not been perfectly precise, but it's the same gradient. Okay, so 3 steps across and 1 step up gives us a gradient of 1/3. If we have a gradient of -3, you can think about that as being -3 over 1, which means our run is 1, so for every 1 step across, we're going to be taking 3 steps down. So we've got a run of sorry, it's not the run, that's the rise, a rise of -3. So for every 1 across, we're going to go 3 steps down. Note that the number 1, -3, so we could think about it as being -3 over 1, or it's the same as 3 over -1. And I want to be clear about those two things are the same thing. So thinking about it this way, we're saying that for every 1 step to the right, we're taking 3 steps down. That's going to be our gradient. Okay. But equally, so 1 step to the right, 3 steps down gives us our gradient of -3. Equally, so I'm just going to put those on that grid so it fits better. Equally, we could have gone 1 step to the left and 3 steps up, which would be how we'd interpret that. But it's still the same gradient. Okay, it's still aligned with the same gradient. Gradient of -3 on 2. So again, that could be -3 over +2, or 3 over -2. It doesn't matter how you think about it, It's not negative on both the top and the bottom. One number has to be negative. So either we think about going 2 to the right and 3 down. For every 2 steps to the right, we go 3 down. Or for every 2 steps to the left, we go 3 up. Okay, so I'm going to go 2 to the right, 1, 2, 3 down. So for 2 across and 3 down, we get a line with a gradient of negative 3 on 2. So having an understanding of what a gradient actually means in terms of what does that mean for the slope? If the gradient's 5, what does that mean about the slope? It means for every 1 step across, we're taking 5 steps up. Now you can always compare it to 1 step across. You can say a gradient of 2 for every 1 step across, 2 steps up. A gradient of a third for every 1 step across, 1/3 of a step up. You can think about it that way instead. But personally, I find it easier to think about it as the whole numbers. You know, for this gradient negative 3, for every 1 step across 3 steps, 1 step across 3 steps down, yes, gradient of, but equally you can also, yes, but also this one, gradient of negative 3 on 2, could be for every 1 step across, it's 1.5 or 3 on 2 steps down. It's the same idea, okay? Again, I find it easier to think about the whole numbers. Okay, so if we have a line with positive gradient, it goes up as we go from left to right. If we have a line with negative gradient, we go down as we go from left to right. If a line has 0 gradient, it is a horizontal line, okay? And that's because if we think about gradient, and we often use the letter M to refer to gradient, gradient is rise over run. And when we have a horizontal line, we have 0 rise, but plenty of run, whether that's, 2 steps across or 10 steps across, it doesn't matter. 0 divided by any number, let's just call it x, 0 divided by any number is 0, okay? So a horizontal line has no rise, but as much run as you want. 0 divided by anything is 0, so a horizontal line has a gradient of 0. A vertical line, however, gradient, think about rise over run, a vertical line has as much rise as you want. 2, 10, 15, 75, negative 30, doesn't matter, divided by absolutely no run, no horizontal change whatsoever. So rise being vertical change, run being horizontal change. Now, any number divided by 0 is undefined. Okay, so for a vertical line, we would say that the gradient is undefined, or it doesn't have gradient. Probably undefined gradient would be the more mathematical way to talk about that. Okay, so let's consider gradient more generally by finding the gradient of the interval AB, so the interval AB being a straight line joining AB, where A has coordinates x1, y1, and B has coordinates x2, y2. Can we talk a little bit about this notation first, because we're going to see this a lot throughout this topic. x1, y1, x2, y2. These are not powers, they're not superscripts, they don't go up here. Okay, they are subscripts. This is not x squared. This is just the first x value and the second x value. It's just a way of us numbering the x values. They're both x values, but they're different, and this one's the first one and this one's the second one. Okay, this is x value number 1, x value number 2. Okay, so can we please be clear about, that not confusing them with powers or as doing anything mathematically. We're just labeling, x value 1 and x value 2. We could probably call it xa and xb. Xa and ya for the coordinates there. X coordinate of point A, y coordinate of point A. We could call this one x coordinate of point B, y coordinate of point B. Okay, it's completely arbitrary. The 1s and the 2s have no value whatsoever. They're just ways of distinguishing between the fact that we've got 2 different points. Okay, so if we think about gradient, okay, gradient is rise over run. So the vertical change divided by the horizontal change. Okay, so rise is the change in the y values. Okay, so if we think about that, it's essentially, it is this distance here between those 2 values. Now that y value there is y2, and that y value there is y1. So if we want to find this purple distance here, we're going to do y2, which is that whole red distance, minus y1, which is that blue distance. Okay, so y2, the bigger y coordinate, take away y1, is going to give us the rise. Now again, I shouldn't have said the bigger y coordinate because actually it doesn't really matter. We'll see that when we talk about the formula a bit more. But essentially rise is y2 minus y1, and by the same logic, the run is going to be x2 take away x1 to work out this distance in between. Okay, so the run will be x2 minus x1. And so therefore we know that the gradient of AB is rise over run, vertical change over horizontal change, which means it's the difference between the y values over the difference between the x values. Okay, now lots of students get themselves really confused and very stressed about which points x1 and y1 and which points x2 and y2. It doesn't matter. Okay, it doesn't matter which point is which. Okay, as long as you are consistent about how you use those points. So these two values, this y value and this x value at the start of the numerator and the denominator, must come from the same point. It doesn't matter which point it is, but they must be from the same point. Similarly, these two values, the y value in the numerator and the x value in the denominator, that come second in the numerator and denominator, they must also be from the same point. It doesn't matter which point, they just have to be from the same point. Okay, that's the most important thing about using the formula accurately. Otherwise, if you jumble them around, you'll get your negative wrong. Okay, it'll be sloping the wrong way. I'm going to illustrate that in this first example. So we want to find the gradient of AB, where A has coordinates 3, negative 2, and B has coordinates 2, negative 6. Okay, so gradient, rise over run, change in the y values over change in the x values. So if we treat this point as x2, y2, and this point as x1, y1, y1, so we're going to have negative 6 minus negative 2, that's the difference between the y values, over 2 minus 3, that's the difference between the x values. Negative 6 plus 2 over 2 minus 3, so that is negative 4 over negative 1, which is positive 4. Now, if we reversed the order that we used the points and we said, well, this one's going to be x2 and this is y2 and this is x1 and this is y1, then we would have instead said negative 2 minus negative 6 over 3 minus 2. And we would have got negative 2 plus 6 over 3 minus 2, which is positive 4 over positive 1, which still gives a gradient of positive 4. Okay, same. So it doesn't matter which order you use the points in, as long as you are consistent about it. Okay, those two numbers have to come from the same point. Those two numbers have to come from the same point. Okay, if you use them the other way around, that's fine, but you can't jumble them up. Okay, you can't have negative 2 minus 6 over 2 minus 3, right? Because then you're talking about the point 2 negative 2 and 3 negative 6, which is not the line that you're trying to find. Okay, I'm not going to do it both ways every time. You don't need to do it twice. I'm just illustrating for you that no matter which way around you use the points, you're still going to get the same values. So I don't ever think about which one's x1 and x2 and which one's y1 and y2. I just think about, right, difference between the y values, this thing minus this thing, and then for consistency, it has to be over this thing minus this thing. Okay. All right, question 2. Now again, you might make the choice depending on what avoids the negative. So actually in this instance, the second one was probably better because negative 2 minus 6 is negative 2 plus 6. So that's nice and positive. Equally 3 minus 2 is also positive. So if we can choose that's often going to make things a bit easier, but still is going to get to the same answer as if we had done them the other way around. Okay, find the gradient of AB where A is negative 1, negative 3 and B is 2, negative 6. Okay, so gradient, sorry, I should have listed that as being the gradient of AB. This is also the gradient of AB in question 2. Doesn't matter which way around I do it. Negative 3 minus 6 over negative 1 minus 2, or, sorry, I don't need brackets there, or you would have done negative 6 minus 3 over 2 minus 1. Okay, whichever way around works for you. Negative 3 minus 6 is negative 3 plus 6 over negative 1 minus 2. Negative 3 plus 6 is 3, negative 1 minus 2 is negative 3, so we've got 3 over negative 3, or if you'd done the subtraction around the other way, you would have had negative 3 over 3, but either way, they give you a gradient of negative 1. Okay, part 3. question 3, find A given that the line segment joining 5A and 10, 12 has a gradient of -1/2. Okay, so we know if we do change in y values over change in x values, we get gradient. Okay, we know that gradient equals rise over run. So in the questions we did in question 1 and 2, it was the gradient that was unknown, and we knew the 2 points. In this case, we know the gradient, we know 1 point, and it's just one of the coordinates that's unknown. So as long as we've only got one unknown, this relationship about gradient is still going to work. So gradient is -1/2, and it's equal to the rise over the run. So difference between the y values, I'm going to do that as a minus 12 over difference between the x values. So the bottom, if I've written a minus 12 on the numerator, I have to have 5 minus 10 on the denominator. Okay, so -1/2 equals a minus 12 over 5 minus 10 is -5. So now I've got an equation to solve. Here's a, I want to get a on its own. A is, we're subtracting 12 from a and then dividing by -5. So the first thing we're going to do is multiply by -5. So we're going to have -1/2 times -5 equals a minus 12. Negative times negative is positive. Half times 5, you know, it's 5 over 1. So it's 5 on, gives us positive 5 on 2 equals a minus 12. A equals 5 on 2 plus 12. 12 is 24 on 2. So 5 on 2 plus 24 on 2 is 29 on 2. Or you can write that as 14.5, but there's nothing wrong with 29 on 2. So A would have to be 29 on 2 in order for the line joining these 2 points to have a gradient of -1/2. Okay, second part of this video we want to look at the equation of a line. So there's a couple of different ways we can be given the equation of a line, and these are the two most common. Gradient-intercept form, which I find students become overly obsessive about and tend to always refer to gradient-intercept form even when it's not necessary or not helpful. Always convert to gradient-intercept form even when it's not necessary and not helpful. So please try and grow some flexibility here about what the equation of a line might look like. So gradient-intercept form is a good form of an equation because it does tell us straight away what the gradient of the line is and what where the y-intercept is. So the gradient of the line, I want to be careful about, again, how you understand this. The gradient of the line is not the first number in the equation, it is the coefficient of x, the number multiplying x. So for example, if your equation was 2 plus 5x, your gradient's not 2 because that's the first number in the equation. The gradient is the number multiplying x, which is positive 5. Okay, and then so gradient, it's m is your gradient, and then the c value is your y-intercept. Okay, I find this really misleading. Students develop conceptions about the y-intercept right here when you learn about gradient-intercept form that aren't correct. The y-intercept of any line or parabola or curve, whatever it might be, is the point where the graph crosses the y-axis. That's the y-intercept. Okay? Now, the only thing we know about the coordinates of the y-intercept, because it's on the y-axis, it has an x-coordinate of 0. So the y-intercept is found by letting x equal 0. Now, when our equation is in gradient-intercept form, if we let x equal 0, m times 0 is 0, and so the y-intercept is c. But what I want you to be careful about is establishing an understanding that the y-intercept is always the number on the end of an equation, okay? Because that's not true. The y-intercept is the value of y when x equals 0. It just so happens in equations in gradient-intercept form, for example, let me put back up that one we had before, when we let x equal 0, we get 5 times 0, which is 0, so it's 2 plus 0, which is 2. Okay, that value gives us the y-intercept. It's not because it's the number on the end. It's not because it's I was going to say something slightly misleading there. It's not because it's a number on the end. It is because it is the value that we get when we let x equal 0. Please don't lose sight of that. Okay. Or we can have an equation in general form. Now, general form doesn't tell us a lot immediately about the graph. These three numbers don't correspond to anything in particular about the graph, okay? But it's often used if we have a lot of fractions in gradient-intercept form. If the gradient and the y-intercept are fractions, we might multiply by a common denominator to get rid of the fractions and write the equation in this form. It's often just a neater way of writing the equation. But equally, it's also very easy to find your x and y intercepts from this form, and we'll have a look at that in the next video when we look at sketching linear graphs. And I really want to discourage you from every time you see this form automatically wanting to change it to this form, okay? This is just as acceptable algebraically and often easier to work with algebraically. It's just that none of these numbers immediately tell you about gradient, y-intercept, etc. Okay, so for example, here the coefficient of x is not the gradient. You would need to rearrange to get y on its own before you could see what the coefficient of x is and therefore what the gradient is. This value is not the y-intercept because when we let x equal 0, that will be 0 there, and we'll have by equals c, and so the y-intercept will be c divided by b. Okay, so but as I said, there are advantages to general form, and you might see an answer given in that form, you might be asked to give an answer in that form. So write y equals, and as I should really say, you know, a, b, and c are usually integers. So by that I mean whole numbers, positive or negative, but whole numbers, not fractions. Okay, so if we want to write y equals negative 2/3 x plus 4 in general form, the first thing I'm worried about is the fraction. I want to get rid of that, and I want to get rid of that by multiplying everything in the equation by 3. So 3 times y equals, now multiplying 2/3 by 3 just cancels out the denominator, so negative 2 times x plus 12. And now we're going to get the x and y terms on the same side of the equation, so I'm going to add 2x to both sides. 2x plus 3y is equal to 12. So these two equations are exactly the same equation, just rearranged into a different form. Question 2. State the gradient and the coordinates of the y-intercept of the line with equation 4x plus 2y equals 3. So we want to convert this to gradient-intercept form because then we will be able to see what the gradient and the y-intercept are. So the equation is currently 4x plus 2y equals 3. We want to make y the subject to get it into gradient-intercept form, so I'm going to subtract 4x from both sides. Just to see it in that more traditional gradient-intercept form, I'm going to write the negative 4x at the start. So I've subtracted 4x from both sides. I'm going to divide both sides by 2, which means dividing everything in the equation by 2. So I'm going to get negative 2x and plus 3 on 2. Okay, so that means that the gradient is equal to negative 2. Okay, that's that value there. And the y-intercept is at positive 3 on 2. We want coordinates of the y-intercept. X-coordinate of any y-intercept is always 0. The coordinates are 0, 3 on 2. We'll talk more about coordinates on graphs, but I want to really encourage you to always label points as coordinates. I know it's a bit of a way off yet, but in your VCE exams, VCAA always specify that gradients should be labelled with coordinates, and if they're not coordinates, then your graph is not correct. Okay, so it's a really good habit to just establish now. Every time you draw a graph, you label everything using coordinates, and then it won't be something that you even think about by the time you get to the end of Year 12. That there is a QR code linking to another much older video I recorded on these same ideas. So if you feel like you need a bit more reinforcement, you can go and visit that video. I'll link it in the description box. The next thing I want to talk about is points on lines. So a point lies on a line if its coordinates satisfy the equation of that line. So it's really important to understand what an equation of a line is doing. So for example, if we have the line y equals 2x plus 1, that's a line with a gradient of 2 and a y-intercept of 1. Okay, and we could calculate that the x-intercept is at half, whatever it might be. Okay, so the line looks something like that. And what the line is the line is a graphical representation of every single pair of coordinates that fit this relationship. So for example, this is the point 0, 1, which means when we let x equal 0 in the equation, y is equal to 1, which is true. 2 times 0 equals 1. This point here has an x coordinate. Let me go a bit further than that. This point here has an x coordinate of 1. When x is equal to 1, y is equal to 2 times 1 plus 1, y is equal to 3. So the point 1, 3 will be on the graph. When x equals a half, okay, y is equal to 2 times a half, which is 1, plus 1, which is 2. That's another point on the graph. When x equals, 1.7, y equals 2 times 1.7, which is 3.4 plus 1, so 4.4. That's a point on the graph. Okay. When x equals negative 3, y is equal to 2 times negative 3, which is negative 6, plus 1, which is negative 5. That's a point on this graph. Every single point on this graph, if you take the x coordinate, double it, and add 1, you get the y coordinate. That's what the graph is. Okay? It's every single pair of x and y values that fit this particular relationship. When you double the x value and add 1, you get the y value. Okay? So, as I said, a point lies on a line if its coordinates satisfy the equation. So, for example, the point 37 lies on the line with the equation y equals 2x plus 1 because when x equals 3, 2 times 3 plus 1 is 7. So, because when x equals 3, y is equal to 7, the point 37 lies on that line. The point 4, negative 2 does not lie on the line 5x plus 3y equals 16 because when x equals 4, if we sub that into the equation, we get 5 times 4 plus 3y equals 16, so it's 20 plus 3y equals 16. We subtract 20 from both sides and we get 3y equals negative 4, and we can find that y equals negative 4/3. Negative 4/3 is not negative 2, so therefore the point 4, negative 2 is not on this line. It's a point, it's fine, it's not an incorrect point, it just doesn't lie on that line. Okay. So when we get asked questions like this, determine whether 3 on 2, 5 lies on the line with this equation. Okay. So when we get that, the important thing I want you to understand is the correct process by which to show this. Okay. You don't know if this point lies on the line. So what you should not do in your working out is immediately substitute x equals 3 on 2 and y equals 5 into the equation, because this equal sign might not then be correct because we don't know whether it's true. We want to test. The correct way to show or to determine whether or not a point lies on a line is to sub one of the values in and then solve the equation to work out the other value and then draw a conclusion from what you find. Okay, so in this case we can either substitute 3 on 2 in for x and then solve the equation for y, and if y equals 5 then the point lies on the line. If y doesn't equal 5 then the point doesn't lie on the line. Or we could sub in y equals 5 and solve to find x. If x equals 3 on 2, then that point does lie on the line. If x doesn't equal 3 on 2, then that point doesn't lie on the line. Okay, so you don't substitute both values in because you're trying to decide whether or not those values make the equation true. You don't know it. Okay, so put one in, solve for the other one, and then draw a conclusion from what you find. Now I'm going to substitute the 5 in because then I don't have to work with fractions. Okay, so we're going to substitute y equals 5. Okay. So we're going to say when y is equal to 5, we get 6x plus 2 times 5 equals 19. So that is 6x plus 10 equals 19. That is 6x equals 9. X equals 9 on 6, which is 3 on 2. Okay. So therefore, since x equals 3 on 2 when y equals 5, the point 3 on 2, 5 is on the line. This is a really important logical process for you to understand. It's really important in a lot of the maths that we go forward to. I've just marked some Year 12 tests where lots of the students are still struggling with this idea of how to set out something like this. Okay, it's not mathematically valid to just sub both numbers in and then hope that the equal sign remains true. Okay, you sub one in, you solve for the other, and you draw a conclusion. Okay. Question 4. The point b negative 6 lies on the line 5x minus 4y equals 20. Find the value of b. Now, this time it tells us that this point is on the line, so we can sub both those values in. We know that for this equation, when x equals b, y will equal negative 6, because we're told it's on the line. Whereas the previous question, we're trying to work out whether or not it is on the line, so we can't sub both values in, assuming that it is. Okay. So this tells us when x equals b, y equals negative 6. So we're going to put that into the equation. 5 times b, sorry, I shouldn't have used the letter b, I don't like it. It often looks like a 6 in the calculations. 5 times b minus 4 times negative 6 equals 20. So that is 5b plus 24 equals 20. I'm going to subtract, so the 24 was negative 4 times negative 6, which is plus 24. I'm going to subtract 24 from both sides. 5b equals 20 minus 24, which is negative 4. And so b equals negative 4/5, dividing both sides by 5. So find the value of b. We've answered the question. B is equal to negative 4/5 if the point b, negative 6, lies on the line, which we were told it does. Okay, question 5. A line with equation y equals mx plus 4 passes through the point 3, negative 5. Find the value of m. Okay, so again, we know this time that it does go through this point. So we know for this equation, when x is equal to 3, y is definitely equal to 5. Put that information into our equation. 5 is equal to 3 times m, m times 3, but it's the same thing, plus 4. So 5 equals 3m plus 4. Taking away 4, 1 equals 3m, and so therefore m is 1 divided by 3. The gradient is 1/3. There are other ways you could find that, but I want you to try and get used to this idea because this is going to work. There's a lot of other options we can think about when we know it's a straight line, because constant gradient, we could work out what gradient has to be if it goes through that point and it goes through the point 0,4, etc., etc. But that method is going to fall apart the minute that this is anything other than a linear equation. Whereas the method I'm using here, which is to substitute the point in for x and y and solve for the unknown value, is going to work for every other function type. Okay, and this is where I want you to start to kind of, shift your thinking towards methods that are going to be more flexible as we move in and extend and look at different kinds of graphs. Okay, the work today is from a mixture of places. So there are some questions from exercise 1F, which starts on page 39, just question 2 and then questions 12 and 13. I then want you to do one question from the building understanding section, which is on page 44 of your textbook, just question 1 from there. And then in exercise 1G, on page 47, I want you to do just every second part of question 2, so 2 A, C, E, G, I, K.